Hello students, in this session we are going to discuss the chapter phenols. Okay, in the last session we had discussed about the alcohols. Today we'll be discussing about the phenols. So the similarity between alcohols and phenols is both these alcohols and phenols contain OH as the functional group, but the main difference is the phenols are generally an aromatic hydroxy compounds in which OH group is attached to an aromatic carbon, that is the carbon atom of a benzene ring or an aromatic nucleus. Such hydroxy compounds are known as phenolic group. Such hydroxy group is known as a phenolic group, and the one condition that is there is phenols are generally aromatic hydroxy compounds. So how they differ with these alcohols? Alcohols are not aromatic, that is the OH group is not attached to an aromatic ring. If the OH group or the hydroxy group is attached to the aromatic ring, then that OH group is called as a phenolic group, and such compounds are referred as phenols. Phenols are classified mainly into three types on the basis of the number of phenolic group present. The simplest molecule, phenolic, this is okay, the compound in which OH group is directly linked to a benzene ring is referred as phenol. So here the OH is linked to a benzene ring, and you all know that benzene ring is an aromatic ring. So if OH group is linked to an aromatic ring, then the OH group is known as a phenolic group, So based on this, the number of phenolic groups or the OH groups that are attached to the aromatic nucleus, so we can classify phenols into three types. One is monohydric phenol, dihydric phenol, and trihydric phenols. What are these monohydric phenols? So these are the phenols that contain only one OH group. This is monohydric. Another molecule is benzene with OH and CH3 group. If OH and CH3 group both are attached to the benzene ring, we call such compounds as cresols. Here OH and methyl group are present at 1,2 position, hence we call them as orthocresols. This molecule contains OH and methyl group. This is also a cresol, but this is metacresol. Because the groups are present at 1,3 position. Similarly, if methyl group is present here, we call it as a paracresol. Another molecule, this is also an monohydric phenol. Okay, all these compounds contain one OH group, hence these are referred as monohydric phenols is what we call them as. Okay, if two OH groups are attached to an aromatic nucleus, then such compounds are called as dihydric phenols. For example, a benzene ring, if there are two OH groups attached, we call such compounds as dihydric phenols. We call them as dihydric phenol. So this is the name of this is catechol. Okay, if the OH groups are present at 1,3 position, this is also a dihydric phenol. So the name of this is resorcinol. The name of this is resorcinol. This is called as quinol. This is called as quinol. All these are dihydric phenols. If three OH groups are attached, then we call those phenols as trihydric phenols. Okay, so these are the phenols which contains three phenolic groups. Okay, for example, this molecule OH, OH, OH. Trihydric phenol. It is also referred as pyrogalol. We call them as pyrogalol. Okay, this molecule. This also contains three phenolic OH. This compound is called as chloroglucinol. Okay, so phenols can be classified into monohydric, dihydric and trihydric based on the number of phenolic group they contain. If a molecule contains one phenolic group, we call it as monohydric phenol. If it contains two phenolic group, we call it as a dihydric phenol. If it contains three phenolic group, we call them as trihydric phenols is what we call them as. Okay, this is the basic classification of phenols. Let us go for the nomenclature of these compounds. Let us see how these compounds are generally named. Okay, let us discuss the nomenclature of phenols. Now, let us take a simple phenol, a benzene with OH group, phenol. It can be also called as hydroxybenzene. It can be also referred as hydroxybenzene. I will take another compound, OH, and a methyl group is there. Compounds containing OH and methyl group are called as cresols. We call them as cresols. So they are present at 1-2 positions. We can refer them as orthocresols. But generally, benzene with OH group is referred as phenol. Phenol. Okay, this is called as the base name, phenol, benzene with OH group. So there is a methyl group present. There is a methyl group present at ortho position. Hence, we refer it as orthomethyl phenol. We call it as orthomethyl phenol. Even if you go for a numbering system, this will be first number, this will be second. You can call it as 2-methyl phenol also. You can call it as 2-methyl phenol. Okay. Now, if this is the case, okay, the nomenclature, benzene with OH group is called as a phenol. You know this. So if there are two OH groups, how it is named? If there is one OH group, we call it as hydroxybenzene. So there are two OH groups. So you can call it as ortho dihydroxybenzene is what you call it as. Even we can go for the numbering system where you can refer it as 1,2 dihydroxybenzene. Okay. If you have a molecule like this, benzene, OH, 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 So you cannot use this terminologies ortho and meta. This is used only if there are two substituents. So there are two groups here. So you should number it 1, 2, 3. So you can number it as 1, 2, 3 trihydroxy benzene is what you can call it as. Okay, you can call it as 1, 2, 3 trihydroxybenzene. So this is how the phenols are named generally. Okay, now the next one is acidic character of phenol. Phenols are generally acidic in nature. Let us discuss when a compound is generally acidic. Why a compound is generally acidic? Consider a compound HA. According to Arrhenius concept, an acid is a substance that releases a proton. Yeah. So if a compound releases more H plus ions, then we call it as it is more acidic in nature. Now the question is, when a compound will release H plus? So there are several factors. One of the factor is if this dissociates, if this releases a proton, it will give you H plus and A minus. Okay, this will release a proton if after the release of the proton, whatever the anion formed should be stable. If the anion formed is stable, that is after releasing a proton, if the anion formed is stable, then this HA will release a proton. So the acidic strength depends upon the stability of the anion formed after the release of the proton. See, after releasing the proton, whatever the anion formed is not stable, then why will this release a proton? So this molecule will release a proton if and only if after the release of the proton, whatever the anion formed should be stable. It should be stabilized due to some effects, electronic effects. I mean, it may be inductive effect, it may be resonance effect, whatever it is. So then only it will be stable. When I take an example of phenol, if phenol releases a proton, it will give you this compound. We call this as a phenoxide ion. This phenoxide ion is stabilized due to resonance. So hope you know what is the resonance effect. So there is a negative charge, single bond, double bond, single bond, double bond, single bond, double bond, single bond. So there is a conjugation here, and you all know that if there is a conjugation here, then what happens? The negative charge gets delocalized into the ring. Hence this negative charge gets distributed. As a result, this molecule becomes stable, because the instability is due to the presence of the negative charge, because negative sign, charge is always a sign of instability. So this molecule will become stable if the negative charge gets delocalized here. I mean, it should become stable. So since oxygen is directly connected to the benzene ring, so there is a conjugation here. As a result, the negative charge gets delocalized into the benzene ring. As a result, the negative charge gets distributed, and this phenoxide ion becomes stable. So since phenoxide ion is stable, so phenol releases a proton. Why? Because after releasing a proton, whatever the anion formed or the phenoxide ion formed is resonance stabilized. That is the reason why phenols are generally stable. So phenols are generally acidic in nature. When you compare the acidic strength of this phenol with carboxylic acids, generally carboxylic acids are more acidic than phenol. But when you compare the acidic strength of the phenol with alcohols, so phenols are more acidic than alcohols. Let us see. Let us take an example of a phenol. This is a phenol. This is an alcohol. This is an hexanol. Both are phenols only. Sorry, both are alcohols only. This is a phenol because here the OH is attached to a ring, but this is not aromatic. So it cannot be referred as a phenol. This is an alcohol only. So what happens is here? In the case of phenol, after releasing a proton, you get this ion, this phenoxide ion. After releasing a proton, you get this alkoxide ion. After releasing a proton, you get this compound, O minus. Look at these three molecules. Out of these three, which is more stable is here. Out of these three, this is stable. Why this is stable? Because the negative charge gets delocalized into the benzene ring. Okay, the negative charge gets delocalized into the benzene ring. As a result, the negative charge gets dispersed and this molecule will be stable. As a result, what happens is phenol will release a proton and they are acidic. But whereas in the case of an alcohol, the anion formed, which we generally refer as a conjugate base. Okay, if this is an acid, then this is called as its conjugate base. Okay, conjugate base is generally formed by after removing a proton. Whatever the leftover is called as a conjugate base. This can be referred as a conjugate base of phenol. So the conjugate base of phenol is stable because it is resonance stabilized. Whereas in the case of an alcohol, the conjugate base, this is the conjugate base, that is the alkoxide ion has no stabilizing factor like this resonance. So the negative charge is not stabilized. So hence, since this alkoxide ion is not stable, it is unstable. So what happens is, since it is unstable, so alcohol will never release a proton. Why? Because after releasing a proton, whatever the alkoxide ion formed is not stable. So why will it release up? Because there is no stabilizing factors like resonance. Hence, alcohols are not acidic in nature. Same is the case of cyclohexanol. Like other alcohols, there is no possibility of this charge delocalization here. There is no, when charge delocalization takes place, if there is an alternate double end single bond, there is no alternate double end single, so negative charge will be on oxygen only. So hence the molecule will be unstable, that conjugate base will be unstable. That is the reason why this cyclohexanol will never release a proton, because it will become acidic if it releases the protons. Why it will not release a proton? Because after releasing a proton, whatever the conjugate base formed is not resonance stabilized. So this is reflected in their pKa values. Okay, so the pKa of ethanol, if you take an example of ethanol, this is methanol, pKa of ethanol is 16, pKa of methanol is 15.54. that is very high values, very high values. Okay, see, smaller the value of pKa, stronger will be the acid. Whereas pKa of phenol, pKa value of phenol is around 8.9. So look at this value clearly, smaller the value of pKa, stronger will be the acid. See, so phenol is more acidic as compared to methanol and ethanol. Okay, so this is about the acidic nature of phenols. Phenols are generally acidic in nature. They are stronger acids than alcohols, but they are weaker acids than the corresponding carboxylic acids. Now, so far we have discussed about the classification, the definition of phenols, classification of phenols, nomenclature, as well as the acidic nature. Okay, so what we'll do is we'll just discuss one reaction of phenols. We need to discuss certain rearrangements of phenols. So hence, in this session we'll be discussing one simple rearrangement, that is Frey's rearrangement. Hope you all know what are these rearrangement reactions. So rearrangement means during this reaction a group from one position migrates to another position. So we call such reactions as rearrangement. Generally, rearrangement of bonds or rearrangement of groups generally takes place. Okay, now phenolic esters. You know what are esters? See double bond O. If this group is there, we call them as esters. We call them as esters. Phenolic esters. When I say phenolic esters, these compounds, there will be a ring. When I say phenolic, so it will be O C double bond O R. C double bond O is there. It is directly linked to the ring here. So we call this as phenolic esters. Phenolic esters, when heated in presence of AlCl3, in presence of aluminium chloride. Okay, aluminium chloride is an Lewis acid. A rearrangement takes place to give a mixture of this OH, C double bond OR, and this group, C double bond OR. This is what you get. So just rearrangement takes place. See, the migration of group has taken place, ortho as well as the para positions. Okay, so this rearrangement is called as Frye's rearrangement is what we call it as. Okay, so it is just the migration of group. A mixture of ortho and para isomers is obtained. In general, low temperatures favors para product, whereas high temperature favors the ortho product. Low temperatures generally favor the para product. Para product is obtained when the temperature is low. High temperature conditions will favor the ortho product. Okay, let us see what generally happens during the reaction, or let us see the mechanism that is involved in this rearrangement. Okay, a very simple mechanism it is. And this phenolic ester O C double bond O R is treated with AlCl3. You all know that aluminium chloride is a Lewis acid. So when acids have tendency to accept electron, what happens is this lone pair of electron, it attacks the aluminium. So a new bond between oxygen and aluminium will be formed, giving this group. Okay, what happens? See, this is O, this oxygen, this is C double bond O R, where R is a linear alkyl group, can take it as. Okay, and this, what you are getting? You are getting AlCl3, right? AlCl3 is what you get, right? So oxygen has donated electron here, so oxygen will acquire a positive charge, and this will acquire a negative charge. AlCl3 minus is what you get, and you get a positive charge on oxygen. Next, what happens? Look at this. This is positively charged, so this bond breaks, the electrons they move here, and this comes out. Okay, this comes out. Okay, see what is happening here. In first step, oxygen is attacking the aluminium chloride, giving this intermediate, right? So these electrons they move here, and this charge gets neutralized. Okay, simultaneously one Cl minus goes off here, resulting in the formation of AlCl2. So what happens is, you get, I'll write it as minus C double bond O R plus. Okay, C double bond OR plus goes off. Okay, because these electrons are moving here, so this will carry a positive charge. C double bond OR plus, right? Now minus, then Cl minus goes from here. Okay, this results in the formation of this compound. You have a ring here, then oxygen, then AlCl2 is what is remaining. This is what you get, oxygen AlCl2, because Cl minus leaves here, as well as this bond breaks, the electron moves here, so this part will acquire a positive charge. This is what you get. Next, what happens? Next is electrophilic substitution takes place, where this group attacks either ortho position or para position. If it attacks ortho position, you get this product. If it attacks meta position, you get this product. So what happens is this will undergo an electrophilic attack, that is C double bond OR plus whatever it is generated. This attacks this, so hence you get this intermediate. As usual, O AlCl2, this is as usual intact. Okay, this is attacking here, that is the electrons will be utilized in the formation of the bond C double bond OR. These two electrons have bond with this, so this part will carry a positive charge. And I hope you know that there will be an hydrogen here. Okay, this is what you get. See, first aluminium oxygen, between aluminium and oxygen there will be a bond formed, then this will carry a positive charge, this will carry a negative charge. So later on what happens, Cl minus goes off here, resulting in the formation of AlCl2, and this positive charge gets neutralized by these electrons, so the bond breaks and a electrophile is generated. So the next step, this electrophile will either attack ortho or para position depending upon the temperature. That is, if the temperatures are low, then it will attack the para position. If the temperature is high, then it will attack the ortho position. This is what you are going to get. Next, what happens is loss of proton takes place, because since there is positive charge, loss of proton takes place, and these electrons they move here. So what you get is here, a double bond is formed. We are left with OAlCl2, C double bond OR is left. Okay, so aromatization takes place. Whatever the Cl minus was there, it will take up this H plus and it will form HCl. So this Cl minus, what it will do, it will take up this and HCl will go off, minus HCl. Right? Okay. Next, what happens is, in presence of water, you get this compound. Presence of water, you get OH, C double bond O R. So this is what you are going to get. Similarly, if the attack take place at para position, similar mechanism will be followed to give a para isomer. So this is what actually happens in a Fry's rearrangement. So in presence of AlCl3, what happens is this group C double bond OR group migrates either to ortho or para positions. Okay, this is what generally happens in an Fry's rearrangement. Thank you.